give like a brief context about the paper. So the paper is called Attention is All You Need. And I can clearly say that this is like the most important paper in AI today. The reason why we
Mm.
have ChatGPT, image models, all of these different things is because we have this paper. And today we're going to like try to understand how it all came about. So we'll read the paper together, have some visualization to like show, to try to explain what is happening. So we'll start with the abstract. So the abstract says that the dominant sequence and structure model are based on complex recurrent and convolutional neural networks that include encoders and decoders. Um, I want to show what they mean. What happened before we had like transformers or attention people was trying to describe was that we have what we call as recurrent neural networks. We had this was what existed before we had like transformers and the current technology that we have today. And the way they worked was that they were sequential. So what it means is that we give it a statement like the cat sat on the mat, right? It's going to process each word at a time. It's going to take the word and it's going to process it and create a vector. Then it's going to pass that vector to the next word, which is the arrow that you're seeing here, to become cat. It's going to like transform that vector and it's going to keep on passing. The idea is that if you have a vector, right, each of these sentences are vectors. It's going to pass through each of these vector and every time that it passes through this vector, it's going to like try to capture the meaning. So that's like how the the RNN was the recurrent neural network. That's how they work, right? So this is like how it works. When you have your final like vector, you're able to like have the softmax and it's able to like predict certain words. We'll get to see this in more detail and more visualization about all of these things. So this was how it worked. But the issue with this is that it's really, really slow. As you can see in the visualization, it to reach the word mat has to pass through all the other words before it can reach the word mat. It means that it's really, really slow. And because we are going sequentially, if you remember gradient descent or gradient descent, yes, propagation, when we are differentiating backwards to uh, to be able to update our weights, right? What happens is that the weights that you are trying to differentiate as you go behind becomes small and small to the point where when it's at this point here, it has lost numbers, it becomes so insignificant. That one is what we call as the vanishing gradient problem. In the sense that sequential, when you look at the forward pass, they all go forward. And there, cat sat on the mat, right? It's only going forward, forward, forward. And this is how you get to predict, right? You get to have a final prediction. But when you want to correct it using backpropagation and you're differentiating backwards, so differentiating backwards, the gradient as you go backward becomes small and small and small. The point where the gradient at this point here is almost insignificant. Becomes very difficult to train. That's like one of the biggest problem with back propagation and stuff like this. So over the years, there have been some adjustments and things have been made to try to improve on this. There's what we call as LSTM. Still, recurrent neural network is a bit more complicated and it's not necessarily needed. But this was like some of the things that were done. So if you remember, like something like Apple Siri in 2010, this was what was powering Apple Siri, and they were quite smart. But they were not as smart as what we have today, right? What we have today is what is powered by transformers. We are going to see. I didn't share this. Let me quickly share this in the group. You can also go through it yourself. You can also go through it yourself. Do you have any questions so far? Question paper, mommy. Okay. So I was similar question. So, but that's like the entire idea. The entire idea is that you are processing each of these words. Even though you are seeing words, the computer is seeing vectors. Um, Hopefully we'll see it in more detail as we go, but each of these words that we are seeing are vectors, and these vectors have meaning. So when you take a vector, you process it to pass to the next vector. You try to like add on it. You can see how we are adding. So this is how the vector talking about is h of t. We are adding as we go on, and we're hoping that the vector that the final vector we are going to have will have meaning, be able to predict the next word. And this method does not really work reliably. So right now, I don't think any big AI model or any AI model uses this anymore. So that's how bad it is right now. So what they are all using is what we call as transformers. They are all using this transformer. This is what powers the attention is all you need paper. The attention you see here, let me quickly go to the image. This is what the attention it is. But this is what the attention is, and all of this combined is what we call as transformer. And that's what many of these AI models are using. For example, when you talk about GPT, GPT means generative trained transformer. And they all depend on the same technology that we are seeing. They all depend on the technology that we are seeing. So going back to the other one, so I spoke about how current name, which is recurrent neural network are sequential, right? For it to process the next word, you need to process the previous word. So before it reaches math, it has to do all the previous words before it can reach math. If you look at the right hand side, attention is different. You look at every word here, every single word here can process the word. So you can see that the word cat, for example, for the math, the word math here, it doesn't have to wait for it to arrive at the right. It can process all previous tokens that came before it. And this is what makes it very fast. That is very is parallel. This parallel effect is what makes it very fast. And that's why it's mostly used today. And we'll see how it works in more detail, right? So you can look at the general knowledge, like to check your understanding and stuff like that. Now we are starting with the first one, embedding and position. Let's go to the paper, right? Let's go to the paper. There are a lot of like gibberish here. We won't really go into like detail because a lot of things are not necessarily needed here. But look at this paper, you see this part here. It's called input and embedding. So what is this part doing? What is this part doing and why is it important? So in this paper, the input here is what we all know as text. It can be anything, it can be the card is on the mat, it can be anything, right? And when you have your text, you do a lot of things before then, but when you pass in the text to to the embedding, what happens here is that you convert it to a vector. Let me show you. Convert text to a vector. Imagine that you have a text screen, queen, and apple, right? What you do is that you convert this text to a vector. Queen can become this vector. It can be any vector, but the idea is that it's a vector. And what makes vector very powerful is that it can convey meaning. And that's why we use vectors in AI and everything. They can convey meaning. So you can see that this is like a small example that we have two different kind of classes. We have fruits and we have royalty and people. You notice that the fruits are vectors too. The fruits are close to each other, while the royalty and people are close to each other. The fact that we can convey meaning through numbers is what powers AI. Because you know that computers only understand numbers. And this whole thing of being able to compress knowledge into numbers is what makes this whole thing very powerful. Like it's so very powerful, even beyond just transformers. Other kinds of AI architecture all fall on the same understanding that you can train a number to be able to, you can train a model, and a model will be able to have an understanding of numbers. Even though I cannot understand the numbers, the AI is able to have like a bit of meaning around numbers. So that's what is happening. So in this first place, have our text, right? And we convert each text to a vector. Vector is what we call as an embedding. That's what this particular part does here. It converts it to an embedding. But the issue with just converting to embedding is that if you just convert to embedding, for example, let's say we have this statement. We have this is our statement, right? We have this statement. This is the first word, second word, third word, and so on. It goes on. Actually, what I would do is that I'll convert each of these words to embedding. I'll convert each of these words to embedding, right? It brings about a very big new issue. And the issue is that, and the issue is that, how does a computer know what word comes first? How does it know that this is the first word? If I go back to the former definition of how things work in parallel. Like, yeah, things were sequential. It makes sense that the words that start with the first word, second word, and third word, they all come sequentially. But when things are done in parallel, right, the computer doesn't know an idea of what word was first and what was not first. Like that's like a very big picture. It doesn't really understand that level of things, like what comes first, because everything is being done in parallel. So even though you're converting to embeddings, right, numbers, it's still very important that you are able to add a sense of position, and that's what we call as position embedding. So we have seen two kinds of embedding, right? We have seen word embedding. Word embedding embeds things into meaning. It's able to attach meaning to vectors. And position embedding, what it does is that it gives each vector a sense of position. What word came first, what word came last. And this is like the algorithm, right? And you can see that for each position, this is how it's going. Let's assume that a vector has 32 dimensions. It simply meaning that it has the two numbers in that vector. And let's say this is position one. Right, this is how position one looks like. Position two will look something different. Right, position three will look something different. And this is just the position embedding of each position. So this is for word one, word two, word four, word five, word six, and as you go, right. Look at each of them having different amplitude and different things coming together. Like they have like different amplitudes. And because they're all different, it means that each position is each position can be uniquely identified. And that's what makes it very, very powerful. And if you later on, you take your word embedding and you take your position embedding, you add them together, you have a final embedding that captures both the meaning and position. This is so impressive on me because one thing I kind of like come to see is that words and vectors are very powerful. People don't really realize how powerful words and vectors are. That you're able to take a word which humans can read, and the computer can convert it to a vector, which will have a very powerful sense of meaning. And because you are dealing with vectors, you can do this kind of operations. You can add things up. And embedding that just converts captures meaning, and embedding that just captures position. When you combine them together, it's going to have a semantic understanding of both meaning and position, which is something very, very, very important and very powerful. So this is what they do here. This is what is happening here. When you are saying this is happening, this is what is happening here. We take our words, we convert them to embedding, we add position, And then we add position, which you can see it there. And the output of this two is an embedding that has both understanding of words and both understanding of position. So the next part that we have to talk about, which is like the main meat of today, the most important part of today is this attention. Was named after attention. So it's very important that we try to discuss attention and what attention is all about. And to go to the paper, we are talking about the paper. This part of the paper we're talking about, yeah, talking about this part. Multi-head attention. We're going to see what multi-head attention is shortly. But the entire goal is this part. I want to understand what this part means. So what does attention mean? This is the formula that empowers all AI. It's just so powerful to like realize that AI is simply just matrix multiplication and clever linear algebra. And this formula is the core formula used in AI today, and we'll explain what it is. So when you look at this formula, you see some attention, right? Attention is a function. It is impure A and V. Pure here is what we call the query. A is what we call the key. And value is what we call the V is what we call the value. So what does each of these mean? So the query here means it's more of like asking a question, right? Think of each word. So one thing I didn't say was that each of these embedding that we spoke about earlier, right? Each of these embedding, they are further transformed into three different more embeddings, and each of them will be a key, query, and value, right? There will be a key, query, and value. So each of these embedding, they will start as one, but then they'll be transformed to three more things. So they'll be transformed to become a key, a value, and a query. That's like what will happen. And so each of these embedding, each of these token, each of these word will have what we call as the going to ask a question. So each of these will ask, okay, what am I looking for? That's the query. What do I contain? And and then the next one is what if you look at me or if you open me, think of it as a container. If you open this container, what will you give? What will you get from me? So these are like this idea of what they each contain. So let's look at how it works. So I explained that. So what happens is I explained that for each embedding that we had initially, we convert them to their respective key, query, and value. This matrix. This matrix is what is embedded into three different things. So for the same embedding, it's going to have multiplied the query matrix. It's going to give a query embedding. That same embedding is going to multiply the key matrix, and it's going to give the key embedding. You need to have the value matrix multiplied with that same embedding, have with the value matrix. At the end of the day, you're going to have three different matrices for the same embedding. What's the first step? In the formula, you can see that the first step is that we multiply the query and the key. So remember that the query is asking a question, and the key is telling you how significant this particular thing is. You multiply them together, you have what we call as a score. I will show you what that means quickly. This is what it means. So this column here you're seeing here, this column here is you can think of it as the query column. This is the key column, right? This is the key column. What happens is that each of these will multiply with itself, like each of these will multiply as we see. So this will multiply with this will multiply with this will multiply with this will multiply with this. and this multiply with this. So they're all going to multiply each other. And you're going to have a matrix like this. And this matrix is what we call as the score. What does it mean? Just telling you that the word for each word is telling you which other word is that important to it. So, for example, the word there, which is itself, is very important. The word animal is very important. Let's look at this one. The word it, for the word it, animal is important and was also important. Okay, for the word it, animal is important, self is also important, right? So what this is doing basically is that when we multiply the query and the key, we have a matrix like this. And it's simply like a dot. So you do this and this and this, and you have this particular matrix telling you how important each of them is. Now, when you have now this, what you now do is that you take your score and you normalize it. So normalizing is just trying to make it a bit more stable, because when you're training AI models, stability is very important. So we just try to normalize it to make it a bit more stable. So that's what we do here. And then we multiply our normalized, our skill score, and we pass it through the softmax function. What does the softmax function do? It does this. So it gives a probability, right? So for each of these rows, it gives a probability, telling you that for the word it, I will assume 40% of it depends on itself, and 45% depends on animal, and the rest of the 5% can be distributed to the other ones. The core idea is that all of these should add up to one. It's telling you that for the word it, 40% of the meaning comes from itself. 5% of the meaning comes from animal. You take any other word, this word is telling you that 60% of my meaning comes from myself, and the other percentage comes from the other one. What does this is what we call as the softmax function. Softmax function. That's what it does. It tries to give like a probability distribution of each of these rows. It's doing like probability distribution of each of these rows. It takes these rows and it gives you probability distribution. That's what it's doing. Now, when you have your scores and you have assigned like probability distribution to each of them, you now multiply it with your value. Remember that the value is what I give you, right? And when you multiply with this, you have like a contextualized output, and this is what you want to have. This output that you have is like the whole essence of what you are doing, like the whole essence of what you are doing. Like it contains the enriched data, and it has to be a bit fast. So that's what it does. Now, what you just saw, we do it many times. So let me show you the diagram. What you just saw is that this multi-attention, what it just means is that what I just explained is done multiple times. So it's done one time, two times, three times, four times, independently. And you now come and you concatenate them. So you see each of these heads simply means the attention that we do. And then you concatenate each of them and you have your final output, which is your concatenated of each of those heads. And then that's what it simply means. When you look at this, multi-head attention means that we are having multiple independent attention, which later on we try to concatenate together. That's like what we have. Now the other ones here are like are more of like stability things. So when you look at like this, right, this is what it means here. It's simply residual connection. So it's more of like stability tricks to make the AI stable to train. These are things that you can go into more detail when you have a bit more time and stuff like that. So for the attention is all you need paper. There's what we call as encoder and decoder. So what is encoder? Encoder is simply trying to capture the meaning. So when you see when you patch your encoder, it's just trying to capture the meaning, and the decoder is what produces generate text. When you look at something like ChatGPT, ChatGPT is a decoder only model. What it means is that it's the embedding and it produces text. While an encoder just produces vector. So that's what encoder means. So encoder is that you give me a text, I'll convert it to a vector. Encoder is you give me a vector, I'll convert it to a text. So for most AI models, you just use the decoder. Right? Some use encoder. Most AI models just use the decoder. Just like what we have, and you have it here. And here I gave like a simple Python code which you can look into. I really recommend that if you really want to understand this, I really recommend when you have time, try to write every line of the code with your hand and try to understand what it's doing. I think that's like the best way you start putting things together and have like a better meaning. So that's like the paper. Most times I don't think you need to read the actual paper. Most times they can be a bit confusing, but I really hope that I really did my best to like make things come alive more. But to be honest, this takes a lot of effort and a lot of difficulty. Like it's not like something that I think you understand in a night. For me, it took me like a month to understand this. So but I would really say that if you are really into AI, as I saw that you are into AI, I would recommend that you take this paper very seriously. Um, um, for most AI projects you are going to work on, I mean like research projects or final, like most AI projects, if you want to go into research and you want to do AI into research, you will use this, you will see this all the time. You see this particular thing all the time. So it's very important for you to like understand what it is and be able to like look at each of this line of code and have like an understanding. Okay, I understand what this means. I understand what this means. I understand what this means, and all of this. So I really recommend that you try to write it down. You try to understand. Try to watch videos. It may take time, but once it clicks, you'll be able to work on more complex projects. So this is like one of the holy grace of AI. Like you look at programming, if you want to do programming, people will give you hello world to type in Python. If you want to do AI, core AI, it's like the hello world of AI. It's complicated, but that's what it is. And it's really, really fun when you get to understand what everything means. And um, later on, you can you can come and you can come and you can later on you can also try to create your own GPT, and it's going to look so similar to this, but it's only going to be this particular decoder.